started as a project of VRC through Variable Energy Cyclotron Committee, and that was chaired by an Indian nuclear physicist, Dr. Ramanna, in 1969. To honor his legacy, VECC initiated the Ramanna Memorial Lecture series in the year 2005. Today, in his birth centenary year, we are gathered here for the 19th lecture in this series. The curiosity about space and universe, it has no educational or age boundaries. It starts with the literature in the childhood itself, when the young ones gaze at the sky and wonders with their rhymes, Twinkle, Twinkle, Little Star, or Chanda Mama Durke. As we grow, that innocent wonder matures into profound reflection, echoed in the timeless words of Gurudev Rabindranath Tagore, Akash Bhara, Surya Tara. And then we take a deep dive into the world of science of quark-gluon plasma, quantum mechanics, astrophysics, so on and so forth. This morning, that same spirit of quest brings together the scientific community here as we look forward to an illuminating session by a very special guest for this 19th Ramanna Memorial Lecture. To start the program, I request Dr. Arup Bandyopadhyay, Chairman, Organizing Committee, for the welcome address. Arup sir.
Very good morning. Dr. Sumit Shum, Director, VECC. Dr. Gautam Chattopadhyay, Senior Research Scientist, NASA, USA, and today's Ramanna speaker. My present and former colleagues who are here, and also many of them have joined online. So I welcome you all in the 19th Ramanna Memorial Lecture. Now, you will listen more about Dr. Ramanna from our director, Dr. Sumit Shum. He was director of BRC during 1972 to 1978, and again between 1981 and 1984. And during his first tenure, that is during 1972 to 78, as Niraj said, the first committee, that is a VECC committee, to consider all the policy matters, including technical design aspects of the room temperature cyclotron, that committee was chaired by Dr. Ramanna. So in that way, VECC has a very deep connection with Dr. Ramanna. Not only VECC, SIP is also having a very good, great connection, because this nice auditorium was inaugurated by Dr. Ramanna in 2004, where we are having our Foundation Day every year and other Ramanna lectures. And as you can make out, it's such a nice place to hold any meeting. Now, another interesting aspect of today's event, as I said, that Dr. Ramanna was the chairman of the first VECC committee. The interesting aspect is the first project which was sanctioned during that time. The first sanction was only for 630 lakhs. You can imagine, compared to the projects what we consider nowadays, although you have to consider inflation or other facts, but still, the first important cyclotron project of the country, the first financial sanction was 630 lakhs, including building and everything. Now, to continue the program, I request our director, Dr. Sumit Shum, to chair the session and also introduce our important guest to the audience. Dr. Sumit Shum, please.
Good morning, dear colleagues, former colleagues, invitees, press and media, students, postdocs, and of course our today's speaker, Dr. Gautam Chattopadhyay. Before I introduce the speaker for today's Raja Ramanna Memorial Lecture, it is customary to say a few words about Dr. Raja Ramanna and the legacy that he has left behind. Dr. Raja Ramanna was a renowned Indian nuclear physicist known for his original research in nuclear fission. He worked under Dr. Homi Jahangir Bhabha and later became the leader of India's atomic energy program. Dr. Ramanna is best known for heading the team that carried out India's first successful nuclear test, codenamed Smiling Buddha, in 1974. As the chairman of the Atomic Energy Commission, he established the Center for Advanced Technology, which is currently known as Raja Ramanna Center for Advanced Technology in Indore, which is now known already to RRCAT. He served as Secretary for Defense Research from 1978 to 1981, Minister of State for Defense in 1990, and member of the Rajya Sabha from 1997 to 2003. Beyond his significant contributions to nuclear science, institutional development, and science policy, Dr. Raja Ramanna was a multifaceted individual with deep interests in music and philosophy. When the K130 cyclotron, that is our room temperature cyclotron, was commissioned in Kolkata, this center, in 1977, Dr. Raja Ramanna described it as an example of thrilling scientific innovation, perhaps even more exciting than the Pokhran nuclear test. At present, VECC has 3 operating cyclotrons. K130 cyclotron has been operating since 1977. Indigenously developed K500 superconducting cyclotron has been delivering the highest energy heavy ion beams in the country to the users for basic science research, and 30 MeV medical cyclotron has been operating for the production and delivery of radiopharmaceuticals to the hospitals and nuclear medicine centers for cancer diagnostics as a societal services to the nation by the Department of Atomic Energy. I was mentioning to my colleagues that since VECC will begin celebrating the golden jubilee of its beam delivery next year, today's event could be seen as a curtain raiser for those celebrations, as this year marks the 100 years of birth of Dr. Raja Ramanna. VECC pays tribute to the great science leader of India by organizing this lecture. Now I come to the introduction of our today's speaker. So it's my great pleasure to introduce our esteemed speaker for today's Raja Ramanna lecture, Professor Gautam Chattopadhyay. He is a senior scientist at NASA's Jet Propulsion Laboratory, JPL, at the California Institute of Technology, Caltech, and visiting professor at Caltech in Pasadena, USA. Dr. Chattopadhyay earned his PhD in electrical engineering from Caltech in 2000. Before that, he completed Bachelor of Engineering in Electronics and Telecommunication from BE College, Bengal Engineering College, in 1987, which is currently known as IIEST. Actually, he is my classmate in the same discipline. He is a fellow of both IEEE USA and IET India, serves as a track editor for the IEEE transactions on antennas and propagation, and is an IEEE distinguished lecturer. His research interests include microwave, millimeter wave, terahertz receiver systems, and radars, as well as the development of space instruments for the search for life beyond Earth. Professor Chattopadhyay has published over 400 papers in journals and conferences and holds more than 20 patents. He has received over 35 NASA Technical Achievement and New Technology Invention Awards. In 2024, he was honored with the Armstrong Medal from the Radio Club of America for his outstanding contributions for the radio science. He also received the NASA JPL People Leadership Award in 2023. He was named IEEE Region 6 Engineer of the Year in 2018 and received the Distinguished Alumni Award from IIEST, the Indian Institute of Engineering Science and Technology, India, in 2017. He has won the Best Journal Paper Award from IEEE Transactions on Terahertz Science and Technology in both 2020 and 2013. The Best Paper Award for Antenna Design and Applications at the European Antennas and Propagation Conference, UCAP, in 2017. The IET Professor S.N. Mitra Memorial Award in 2014. And the IET Biman Bihari Sen Memorial Award in 2022. He is the 2025 President of the IEEE Microwave Theory and Technology Society, MTTS. Today, he is going to talk on space exploration and our place in the universe. This is a topic of contemporary interest, particularly after, say, Shubhranshu Shukla's return from the space, and India is gearing for its Gaganyaan mission. So I invite Professor Chattopadhyay to come on stage and deliver the 19th Raja Ramanna Memorial Lecture. Professor Chattopadhyay, please.
Good morning, everyone. What a great honor for me to be standing in front of you today. I'm really humble because this is Meghnad Saha Auditorium. As a kid, growing up in Novogram, not too far from here, we used to dream about Meghnad Saha. These people are made of dreams. And standing on a stage in his name, I'm really getting goosebumps. I'm really humbled. And today I'm going to talk about some space exploration and our place in the universe. Of course, the title is big, it covers a lot of things. So let's see what we can learn together. So can I have my slides? Okay. So as I want to thank my good friend Shumit Shom. Shumit and I, we actually studied together in B College in the EPC department. I'm not going to talk about his exploits as a student in college, it would be embarrassing, so I spare you that. I'm the president of the IEEE Microwave Theory and Technology Society for 2025. Uh, IEEE is the largest professional organization of the world of electrical engineers. We have more than 500,000 members all over the globe. And Microwave Theory and Technology Society is one of the societies where we have more than 16,000 members. And I'm very proud to be the first Bengali to be the president of such a society, global society. So I actually read so every year, when as a president we choose to select the theme of the society for that year, and I chose the theme, Dare Great MTTS Future Together. I want to emphasize on the word together because it's very important for all of us. And particularly a place like VECC, we have to work together because these are multidisciplinary endeavors. And now more than ever, given what is going around geopolitically, I think it's very important that we all work together. I think this one is not moving forward. Front and back. Oh, it's on. So as I said, MTT society is a very large society, global society. So I want to just show one or two things. I will urge all of you, if you are an electrical engineer, you should become an IEEE and MTTS member. And this is the QR code because nowadays you cannot get QR codes. I mean, everything that is everywhere QR codes. And as well, we have a 50% discount for membership right now. I think everyone likes a discount, more than tariffs, right? So what we do, MTTS actually does field of interest in the very broad sense. What we do here at VECC also comes under that. Megahertz to terahertz community, we are working on artificial intelligence, quantum technology, semiconductor technology, and all this. So, but I want to start with this. This is the blue dot. This picture was taken by Voyager spacecraft in 1990 on Valentine's Day. How romantic. And what we are looking at is this blue dot. And looking at it, very famous astrophysicist Carl Sagan has said, that's here, that's home, that's us. Our planet is a very fragile planet. And this is the only place that we know so far that life exists. That's why we have to take care of it. I want to show another picture. This picture actually was taken from the surface of Mars in 2014. And this is the first time our planet Earth was captured from the surface of another planet. If we expand, what we are seeing is the moon and our planet Earth. Why I'm showing this, I know there are a lot of students here, because sometimes we think that we know everything. We are very big. We have all egos. But whenever that kind of ego comes over as a student, I want you to think about this photo. Because in the big scheme of things, we are just a dot in the sky. However, we are actually not really taking care of our planet Earth. I'm going to show you a video. This is the surface temperature of planet Earth from 1880 to 2024. This data was actually put together by NASA. And you are going to see how the surface temperature of planet Earth is changing. You can see I put it in faster. As we go forward and we stop at 2024, I want to stop it here. Keep it on the screen for some time for you to realize what is happening. Look at where we are now. This is not sustainable. The blue dot that I showed you might not exist if we don't do something about it. And for the first time, our surface temperature of the Earth actually increased by 1.5 degrees. We have to do something. As a scientist, as an engineer, as a global citizen, it is upon us to do something. And we can do. We develop technologies. So I urge all of you to think, what can we do together? So that's why this year, as the president of the society, I actually started these microwave technologies for sustainability, how we can help. What can we do? We develop radar, we develop sensors, we can provide data. So I urge you all to join us in this. Okay, let's now talk about what we actually on the title. What do we do with their mighty things? We are studying our home planet from air and space. We are looking for life beyond planet Earth. We are creating robots where humans can go. And also we are exploring our solar system. I want to show you this picture. This is Voyager 1 that was launched in 1977. Think about when it was launched. Right now, Voyager 1 is actually 22 light hours away, not years, hours, which translates to about 25 billion kilometers. This is the farthest a man-made object has ever gone. It has gone beyond our solar system. If you compare the distance between Sun and planet Earth is 150 million kilometers. So this is 25 billion kilometers. And still communicating with us. Of course, it is not sending YouTube videos, it's just sending few bits saying I'm alive. I'm still here. This is amazing engineering feat that it can still communicate after all these years, because we have used 1970s technologies, not modern day technologies. So that's what we can do when we are building things for lasting. So I want to start with the Big Bang Theory. This is not the Big Bang Theory you watch on TV. So this is the real Big Bang Theory. We believe that our universe started with the Big Bang, and the current age of the universe is about 13.85 billion years. And when we actually study our universe, going back in time in electromagnetics, we can go back only up to about 280,000 years after the Big Bang, because that's when the first light of the universe came out. It's called cosmic microwave background radiation. You can see that there's a microwave term in that as well. And it was discovered in a very interesting way. Two scientists, Arno Penzias and Bob Wilson at the AT&T Bell Lab, they are doing some communication experiments. And when they're doing the experiment, they are finding in the receiver system the little bit extra noise that they could not explain. Wherever they look, they are finding a little bit of extra noise in their system, little bit extra signal. So we do experiments in our lab, right? And when we do some experiments and find something that we cannot explain, what do? We always think it must be experimental error. And we just make the error bar slightly large and say we are done. But they are smart on that. So they started thinking about it, and they went and talked to a physicist at Princeton. Then they realized that what they're looking at is the first light of the universe, cosmic microwave background radiation. And for that, they went on to win the Nobel Prize in Physics in 1978. So before the students here, I'll tell you the next time you do an experiment and you cannot explain something that you measure, don't think it is an experimental error. You never know, you might win a Nobel Prize. So talking about Bob Wilson and Nobel Prize, I want to show this picture. I'm very proud of this. This is in November 2024 in New York City. I'm with Bob Wilson. I actually was very fortunate to receive the Armstrong Medal from Bob Wilson last year. And he's a very humble man. He also did his PhD from the same place I did my PhD. We are alumni from Caltech. So I was very happy. And this Armstrong is actually not Neil Armstrong. This Armstrong is Edwin Howard Armstrong. He is the inventor of AM FM technology, FM radio, that you Radio Michi that you hear, listen to. He is the inventor of that technology, and in his name, Radio Club of America has this award. So I was very fortunate. I could not help showing this photo. So at NASA, we are doing all this stuff. We are trying to understand how the universe works. The main thing for us is about science. You hear about NASA doing all kinds of technological stuff, but main driver for us is answering science questions. And one of the biggest science questions today is, are we alone in this universe? Is there life beyond planet Earth? Of course, many of you read on the internet or see on YouTube about aliens, right? I just wanted to make sure that you understand we have not found any form of life anywhere outside our planet Earth, not even a single cell. So next time your friends talk about aliens and say they have found aliens, please ask them to talk to us so that we can stop spending billions of dollars. But the question is there possibility of finding life outside our planet Earth? Actually, if you ask me, I think yes. Let's do a thought experiment. When you look in the sky, we see our Milky Way galaxy, that is Akash Ganga, you call it. We have about 400 billion stars, order of magnitude, in our own galaxy. And in the universe, we have about 100 to 200 billion galaxies. So if you do your math, you know that we have trillions and trillions of stars out there. And we are finding majority of these stars, they have planets around them. And not only one, they have multiple planets. Like our solar system, they're called exoplanets. So far, we detected about 900 kind of exoplanets. And we are finding many of them, can sustain life. They're in the habitable zone. So when you are talking about life, we talk about our kind of life, hydrocarbon-based life, that needs water, that needs oxygen. Then you might say, there could be other kind of life. Why don't you search for that? Absolutely, but how do you search for it? At the beginning of this event, someone mentioned about Rabindranath Tagore and Akash Bhara Shuddhata. So I want to actually quote one line from Tagore, because when I'm in Kolkata, a Bengali, how can we avoid Tagore? What is science or whatever it is? So in the line of that song is, Janar mache ojanare korechi sandhan. It's very important. It translates to, we search for the unknown, the knowledge of the known. When you're looking for life, we have to search for what we understand. We understand about hydrocarbon-based life. So we might stumble upon other kind of life, but we cannot actively search for it. And that's why we are actually looking for hydrocarbon-based life. When we say about habitable zone, we mean that the planets which are the conditions are such that the water can exist on the surface at room temperature. We are finding many of them. They have to be rocky planets. It cannot be gaseous giant. It needs to have an atmosphere. It needs to have chronos, carbon, hydrogen, oxygen, nitrogen, phosphor, and sulfur. These are the building blocks of life. We are actually looking for that. We found some planetary system nearest one that is 4 light years away. It will take 40 million years for us to go there. So we cannot really go. So we are building the next generation of instruments so that we can learn more about them. That's what we are doing. So our technology is not good enough to do all of this stuff. So I am here talking to you. Please join us so that we can actually develop the next generation of instruments. But what is the possibility of life in our own solar system? Look at this picture. This is actually Enceladus. Enceladus is the moon of Saturn. What you're looking at is water gushing out of it. It's a very cold planetary body, and this actually was detected by using an instrument called Herschel Hi-Fi instrument, Herschel Space Observatory. And I was very fortunate to be part of the team who developed that instrument, who made this detection that water is gushing out. It's a very cold planetary body. If water is gushing out, it has to have some source of energy inside. So water is coming out. What else is there? We don't know. So NASA is actually planning a mission to go there and find out, is there any organic materials? Is there any life materials out there? We don't know. Another very interesting planetary body is Europa. Europa is the moon of Jupiter. And what we know is that it again is a very cold planetary body. However, the scientists believe that there is a liquid water ocean underneath the thick ice shell. The thickness of the ice is about 15 kilometers to 100 kilometers. If the liquid water ocean is there, that means there is a source of energy. If there is water, if there is source of energy, can there be life? We don't know. If we came to you and said, okay, we are sending an instrument to find out if there is life on Europa, what kind of instrument you are going to send? The obvious answer will be, we send a drill a hole, lower a bucket, and see if there is any fish. We like fish here in Bengal. Unfortunately, when we send an instrument to this kind of places, total amount of power available to us is about 400 watts. 400 watts is 4 light bulbs. So how can you have a drill with 400 watts that can drill through 15 kilometers of ice? So is that not going to happen? So you'll have to think outside the box. Actually, NASA launched a mission to Europa called Europa Clipper last year, 2024. And it has all different kinds of instruments. We have a GPR, ground penetrating radar, so that you can find out what is that, what is there in that ice shells. We have spectrometers, very high resolution spectrometers to find out what is coming out on the top surface. However, Europa is very close to Jupiter, and Jupiter is very high magnetic field, very high radiation environment. So what radiation does is actually sputters all the surface materials in the atmosphere. So we are actually trying to find out if there is organic materials coming out. Organic does not necessarily mean life, but it's precursor to life. But it takes 7 years to go to Europa. So we'll have to wait for 7 years to find out what we are finding. So this is very challenging. Space exploration is not easy. And you all know that we keep going back to Mars. Why? Because Mars is our closest neighbor. But at the same time, if you look at the early history of Mars, Mars resembles very much like our planet Earth. But if you go there, we have not found life on Mars. But the question is, was Mars ever habitable? Is there life on Mars today? We have not found anything. That's why we keep sending all these rovers. The first one, a small one, we sent in 1996. Then in 2003, we sent Spirit and Opportunity, and to 2011, Curiosity, and the most recent one, 2020, we sent Perseverance rover. This is Perseverance rover in our lab at JPL, just before it was sent for launch. It is one of the most expensive self-driving cars. It drives on its own, but it has all kinds of really cool instruments. It is doing a lot of great experiments, and we are learning a lot about Mars. And landing on Mars is not easy. Only a few nations have been successful in landing on Mars. Why? If you look at this, how this launching of Mars happened. So there is a window of opportunity every 2 years to send any spacecraft to Mars, because that is the time the distance between Earth and Mars is the closest. So what happened is, when we launched this Perseverance rover, you can see here on that where the Earth was, the blue circle is the orbit of Earth, and the orange one is orbit of Mars. And the yellow one is the orbit of a spacecraft, the Perseverance rover spacecraft. So you can see the distance, how the distance was. You have to do precise calculations. When actually the spacecraft is traveling, the speed is about 70,000 kilometers per hour. So it has to arrive at the top after 7 months. You can see here on the top of that orbit, just before Mars comes there. Because if we arrive a little late or earlier, we'll miss each other. And we have to slow down, because at 70,000 kilometers per hour, we cannot enter the orbit of Mars. So we'll have to slow down to about 20,000 kilometers. And unfortunately, Mars atmosphere, density of Mars atmosphere is only about 1% of planet Earth, which means it doesn't slow down that easily. So we have to do a lot of maneuvers and enter the Martian surface, the atmosphere at a precise angle of 11 degrees. So then we launch, we have some parachutes, and we'll have to do some sky cranes and everything. Then we go on the surface of Mars. It's extremely challenging. Last, a decade or so, we have been very successful there's no mishaps. But before that, there are a lot of mishaps. We learn from our mistakes. It is never routine when we launch anything to Mars. So if I show you this picture and I tell you that some of this picture is actually some roads in Calcutta now, you might believe I actually came from Kunnur and going through some of these roads. But no, these are all from Mars. I want you to have a close look at them. So if you see them closely, you'll find that some of the terrains that you are seeing there is possible only when there is flowing water. If you go to Mars today, you don't see any water, not on the surface. But the question is, what happened? Where did the water go? Can it happen to our own planet? And what can you do to, mitigate that? So these are the big, important questions that we are struggling to answer. And talking about water and talking about life, I talked about technology. There is very important thing about water, that scientists believe that Earth's water might have come from comets. It is one of the most intriguing questions that how our solar system water came, how Earth's water came. So one of the hypotheses is comets brought water to Earth. If I tell you that you, as an engineer scientist, you are going to ask me, how do you prove that? It turns out that water has colors. Of course, we studied in our high school that water is a colorless, odorless, liquid. What I mean by color is different frequencies associated with them. There are different kinds of water. The water that we drink today, H216O, hydrogen, two hydrogen and oxygen has different isotopes. The most stable one is H2, that's 16. The most abundant water is H216O. But there are other kinds of water, H217O, H218O, HDO. One hydrogen, one deuterium, one oxygen also makes water, and heavy water we all know. If you take the ratio abundance of different kinds of water, it turns out that our planet Earth's water is very similar to some comets called Jupiter family comets. And if you make the ratio of D/H, that is deuterium over hydrogen, that ratio tells you from where is water coming from. However, we have made only about 10 such measurements so far, not statistically significant enough. So I came up with this idea of an instrument. I call it Water Hunting Advanced Terahertz Spectrometer on ultra small platform, a mouthful. Acronym is WhatsUp. Because what we are trying to answer is what's up with water. So what we are trying to do is we are trying to build an instrument in a shoebox sized satellite, about 30 centimeter by 20 centimeter by 20 centimeter, very small. So if you can make a very high resolution spectrometer that can measure with very high precision all these different water that I mentioned and take the ratio, and you can do multiple cometary measurements, then you will be able to answer for once and all. The comets brought water to Earth. So how do you go about building an instrument like that? Many of you are actually working at VECC, build instruments, so it will be interesting for you. Because whenever you start building anything, you start with a block diagram, right? So this is the block diagram of the instrument, WhatsUp instrument. It is a 500 to 600 gigahertz heterodyne spectrometer. When I say 500 to 600 gigahertz, you are thinking, what are those frequencies? Everyone has a smartphone here, I know. And your smartphone, you use Wi-Fi, you use Bluetooth. The frequency of this Wi-Fi and Bluetooth is about 5 gigahertz, in that range. So we are talking about 2 order of magnitude higher frequencies. When you're trying to build an instrument at this frequency, it's not easy. So let's see what we need to do. So idea of that is we will have to build an instrument that has to be very low mass and power. If you look at current generations of instruments that can do this kind of stuff, that is bigger than this desk that I'm standing in front, weighs a lot, draws a lot of power, but we cannot put that in a shoebox-sized satellite. So our target is to build that instrument with 2 kilograms of mass and less than 5 watts of power. 5 watts is your 5 night lamps. How do you build that? So what are the challenges? So when we are building something, what we start doing is we look at what are the technology gaps. So what we need? We need an antenna at this frequency so that it has to be very low profile so that it can fit in that small satellite. The next thing that we need is a calibration, because whenever you do measurement, we need to first calibrate our instrument. Otherwise, how do you know that 1 watt is 1 watt if you don't do a calibration, right? How do you do calibration? One of the ways to do calibration for instrument is called Dickey switch method. What we do is first we look at a known object, let's say known load, and then we measure what we get, and then you switch back to the object that you are trying to measure. That way you can actually calibrate against your known load. Unfortunately, at this frequency, there is no low loss switch available. You cannot buy it anywhere. It does not exist. So that is a technology gap. Next thing you need is a synthesizer. Many of you know synthesizers are used for musical instruments. The same thing, only thing is frequency much higher. A 90 gigahertz synthesizer, if you actually try to see in your lab, it weighs 20 kg and draws more than 25 watts of power. You cannot use that. So what do we do? That is a technology gap. Then we need a spectrum analyzer. It's a spectrometer. Spectrometers, I don't, many of your physicists, you know that very well, but if you are not, you remember in your higher secondary, at least we did those experiments during our days, we actually used the sodium Hepal line and try to find the spectrometer line. This is a spectrum analyzer. We are trying to measure the frequency and what is the power. If you buy a spectrum analyzer in the market, again, it weighs 15 kilograms and draws more than 20 watts of power. We cannot use this. So these are our challenges. So we started working on different aspects of it. First, we actually looked in the antenna. We have been developing a lot of different antennas, deployable antennas at NASA. One of them I'm going to show, actually my postdoc, and I really worked on that. It's a 30 gigahertz, not at 500 gigahertz antenna. This is a deployable antenna. I have a video, I want to show you how it works. Basically in space, there is a spring, we release the spring and it deploys. You can see here, this is the mesh reflector kind of antenna. Just like your umbrella that you used coming in here, right? And then, but there is high precision. There is a sub-reflector that gets deployed, and there is a horn antenna that just acts as a feed. It works great. We actually went to space in a rain cube called the mission, and working great. However, it cannot work at 500 gigahertz because the surface accuracy that we need, we cannot get in this kind of antenna. So we actually came up with all different kinds of antennas. I'm not going to spend a lot of time, but meta-surface antennas, we used a reflector antenna, very low profile. You all know reflector antenna because on your dish antenna that you see on your rooftop, they are reflector-based antenna, but they take a lot of space, volume. We cannot use that in space when I'm making it very small. So we came up with a very innovative reflector antenna. We have a patent on that, and also we made a lens-based antenna. This is a very thin silicon lens working at 600 gigahertz, but very low profile and weighs less than 500 grams. And we tested everything and put it together, and it works great. That problem is solved. Let's look at the problem for our switch. I told you we'll have to go one by one. As I said, switch doesn't exist. Many of you have done physics and know about waveguides. Waveguides are actually high-pass filters. So if you change there's a cutoff frequency for waveguide. They are metal pipes. So TE10 mode, this is the only equation I'm going to use. TE10 mode for cutoff frequency for rectangular waveguide is C over 2A. A dimension is the A of dimension of the waveguide. Now if you change the A dimension of the waveguide, then it can turn the waveguide on or off. So that is the technology we have used. What you are seeing here on your screen, this rectangle, orange rectangle is a waveguide, metallic waveguide. The dimension of that waveguide is 250 micron by 500 micron. That's why this is under the microscope. You say, what do those dimensions mean? Thickness of your hair is 150 micron. So we are cutting metal with a piece of hair. That we have done. So these waveguides are like that. So you are able to make this kind of stuff. And what you are seeing, there is a main structure and there is a septum that will go in and out to make one of the waveguide cut off so that it's off and the other one is on. I'll show you a video. This is again the videos taken under microscope. We just actuate the MEMS and it goes like this and we can make it a switch. Very low loss switch, waveguide based switch. And it worked great. Again, we have a patent on that. So that's what you'll have to do. You'll have to solve problems. We also made some other kinds of switches using piezoelectric motor. I'm going to skip that. But again, you also make a switch like this. This is a different kind of switch. What happens is that the U-shaped waveguide that goes, you can move them, and then it becomes one turn off, the other turn on. Talking about the synthesizer and spectrum analyzer, as I said, that you cannot, if you buy them, that weighs too much. So what we did, we developed SoC called System on a Chip. Have you opened your smartphone, anyone here? I don't see any hand going up. I opened my wife's phone. Okay, it was water damage, that's why I opened it. But you should open your smartphone. What you are going to see there is all these SoC, System on a Chip. So in the past, we used to make chips that used to do only one function. But nowadays, one chip actually does a lot of different things. So what we did, we designed our own SoC, System on a Chip, using CMOS technology, your cell phone technology. That actually makes a 90 gigahertz synthesizer on a single chip. You can see here that picture here behind me, the red one. So chip is just there. And it was great. It draws only less than half a watt of power. As I said, if you buy something of this frequency, it's not available, but it will draw 20 watts. And we also built a spectrometer, spectrum analyzer, that draws 1.6 watt, exactly the same way, using SoC. So if you innovate, you'll be able to make this kind of improvements. And then you have to put everything together. Integration is a big challenge for instruments. So what we did for WhatsApp is, you can see we built two versions of the instrument. One is with the reflector antenna on your left. You can see here. But what you are going to see is on the top, you see the synthesizer, and then we have some detectors. There are Schottky diode detectors. We have the switch. So everything put together. This is for comparison. You can see I said the previous generation of instrument was this big. But now you can see on the desktop how small that entire instrument is. So we wanted to actually, we tested this instrument in our lab, but we also wanted to test it in the balloon-borne instrument in the sky so that we can see what we are going to get. So we put it on a gondola here, you can see here, all the gondolas. And again, just before launch, we are here. And then we launched it from a place called Palestine, Texas. And it's a very high-tech balloon launch. You can see here that we are holding the instrument by hand. So we release the balloon. And then you can see there behind, we are actually running with our instrument. This is not your traditional NASA launches. So we just release that, and it goes up to 120,000 feet in the sky, and then we get all the data. It is very important that you test your instrument at relevant environment, and that's what we do. And here you can see that this is the flight path. We launched from Palestine, Texas, and the balloon came down near Dallas. So this balloon had a parachute so that the instrument comes down very slowly on the ground, Unfortunately, our parachute didn't work very well. So the instrument came down at 65 kilometers per hour. It crash landed on the ground. So we recovered it, you can see here, it's on the ground. We recovered it, brought it back to the lab. We found the thing that came out was the lens antenna. And we turned it on and everything was fine. Everything was working as is, even after the crash. For NASA launch, we'll have to do a lot of tests. We'll have to do thermal back tests, vibration tests. One of the tests we also do called shock test. We'll have to really shock our instrument. After this, we don't need to do a shock test for our instrument. Our instrument survived the shock. And look at the data. I want to show you the data as well. Because at 120,000 feet, we wanted to measure the water isotopes, right? But water is pressure tolerant, too much at 120,000 feet. This is not vacuum. That's why you cannot really measure water, very high resolution water from 120,000 feet. So we actually measured ozone instead. And you can see here, this is a measured data of ozone at 544 gigahertz. And this is the model of ozone, how to look at that altitude, at that condition. So it worked great. So what's the next step? Idea, as I said, that we want to go to multiple comets. So in the future, we are just waiting to get a ride. In the future mission, when they're going to go to Mars or anywhere else, on the way, they will throw us out. Our instrument will have our own propulsion system. It will go to those comets, do the measurement, and send the data back. And we'll be able to answer for once and all, did comets brought water to Earth? So we're just waiting to get a ride. Next time I come here, maybe I'll be able to tell you the answer that whether we are able to answer that question or not. Before I end, I want to talk in a few minutes about another instrument, Mars helicopter. Many of you know that we actually flew a helicopter on Mars called Ingenuity. This is the Mars helicopter. So you might ask me, what is the point? Why are we flying a helicopter on Mars? When we send a rover to Mars, the rover has limited mobility. It cannot go everywhere, right? And it takes about 13 minutes to send a signal from Earth to Mars. So we cannot do drive from here. So idea was that can we actually fly something, a helicopter or a drone on Mars, so that it can take off from there, it will go around, do those measurements, some measurements and send some data back to the rover, and then the rover will go to those places and do experiments. So that is the idea. But you might ask, what is the big deal? Because we see helicopter flying here all the time. The big deal is that, as I said, the density of Martian atmosphere is 1% of planet Earth. So when a helicopter flies here, the rotor blade, it rotates at about 400 RPM, revolution per minute. But to get the same kind of lift, the helicopter in Mars has to rotate at 3000 RPM. Extremely challenging for something that is small to have to rotate at that very high speed. So we thought, okay, let's try to make a helicopter and see. This was supposed to be a tech demo that we can do something like this. So idea was that we will have 3 to 4 flights. So we put together, again, the nominal flight will be 2 to 3 minutes. The range was about 600 meters that you can go, and only about 40 meters above ground, because beyond that, the atmosphere gets even thinner, so that we won't have that kind of lift. So this is a completely autonomous vehicle. It has blades, actually, total mass of 1.4 kilogram. Also, it has own solar panel. It has gyroscope and everything. So we mounted our helicopter under the belly of the Perseverance rover. And what you are seeing here is actual picture that was taken by the camera mounted on the Perseverance rover. This is Martian, surface. And the helicopter was lowered to the ground, and you can see that it actually moved away. The rover moved away. You can see the track marks. and the rover was standing about 40 meters from that helicopter. And Mars atmosphere goes through a lot of temperature cycles. It's cold, it gets really cold. And we did not know our little helicopter will survive that atmosphere or not. And this is the first time the helicopter was actually standing there on its own. And there is a video camera mounted on that rover, and it got a video. This is the video, you can see, this is the helicopter here. This is the first flight of the helicopter. And you can see behind the Martian mountains. And it took off. It was actually 90 seconds flight and made a turn about 92 degrees. And then it came down. So for the first time, here we flew something on another planet. And you can see that it will come down, and it was a success. It was a great success. And as I said, that we thought that it will fly 3 to 5 times, and so okay, we can do it. So we try to break this little instrument. We try to go as fast as possible. We try to go as high as possible. We try to go as far as possible. But this little thing refused to die. We had 72 flights, planned only 5 flights. The highest altitude it went about 80 feet. We had total 128 minutes of flight, 2 years of lifespan. So ingenuity on January 18, 2024, about 1.5 years ago, while landing, there was a big boulder, so it clipped one of its wings with that boulder, and it actually died. I am showing this to you all to show the ingenuity of human spirit, of human engineering and technology development. Because when we actually put our minds together, when we put our heads together, we can achieve amazing stuff. And with that, I will end. Thank you so much.
I think we will take some questions. So anyone would like to ask any questions, please?
You want to have any questions?
Yeah.
Okay.
Some of the pictures of the Mars,
Yeah.
the background is the clouds.
Yes.
So, I don't know, is that water droplets evaporated?
Thanks a lot for the nice talk, but and then just want to know that in some of the pictures of the Mars in your beginning of the slides, we've seen that this, and one more is that for testing of these kind of instruments which you build, so those we can't test with the rockets, or means why you try to blow with the balloons or
Yes. Okay. So there's 2 parts of the question. First question was that when some of these photos we see there's kind of cloud kind of thing. So what are those? We don't have much, water vapor on Mars. Those are actually dust storm, because Mars has a lot of dust, and also there are a lot of wind that flows there, and there is a dust storm happens. So most of them, what you are seeing there, are actually dust particles. Very little water vapor. The water vapor is very low. And the second question was, okay, how do you test this kind of stuff? Do you have to send it on a rocket? So what we'll have to do is create that relevant environment in our lab itself. For Mars, the helicopter, as I said, Mars gravity is lower than planet Earth because the mass is smaller, and also atmosphere is only 1%. So we created in our lab a semi-vacuum system where the atmosphere was about 1% of what we get on planet Earth, and also it was mounted on a gyroscope so that it gives you the kind of the gravity that we can experience, and then we test all this. So we'll have to do rigorous tests, because you cannot really send everything in, launch them and then know what works, what doesn't work. Because in NASA parlance, of course, ISRO parlance, one of the things is failure is not an option. So we'll have to really test very rigorously to make sure it works.
Any other questions?
Okay.
Renu?
Yeah.
So we are actually talking about a lot about the global warming and to arrest it or something. But don't I thinking that it is actually the ultimatum. I mean, maybe we can arrest it for a few more years or something like this. And in this scale of the universe, I mean, it is probably not much. Or is there any work, or is it not right that we should get habituated, or how do we get habituated with this global warming or the atmosphere that is coming in the next
So the question was that, okay, what is the point in trying to arrest this? Let's get habituated to that, similar kind of stuff. So of course, then we'll have to let it go. I think in human spirit is, we don't let that happen. This is the only place, of course, many of you think that we'll go to Mars and colonize it. You read in the newspaper. Why would you leave the only place? It's a beautiful place to live. If you go to Mars, it is not easy to live there. As I said, atmosphere is only density 1%. You'll have to wear an oxygen mask all the time. You'll have to wear, because of the thin atmosphere, these cosmic rays and all, you'll have to wear an astronaut suit all the time. You won't have to, you won't be able to run around in rain here the way you do. So what we have to do is trying to find out what can we do. What is the underlying reason for what is happening, the climate change that is happening. And if you actually start studying that, we'll realize that a lot of things that we can do ourselves. So that we might be fine, but our next generation might not be fine if we don't do anything. So we'll have to do something.
Yeah. Actually, my point is not that to stop doing that, but in parallel also that
whether we do anything or not, we are getting used to this, right? Extreme climates. You can see here number of thunderstorms, number of lightning increasing. The reason is because of the rise in temperature, of the surface temperature and the water temperature. That's one of the reasons. More people are dying. So it is actually, even if we get used to it, we can see what is happening. The extreme conditions are coming more and more. So we'll have to really do something about it.
Thank you very much for a very nice talk. So my question is that, how you are detecting the different isotopes of the oxygen? So that is kind of vibrational motion of the hydrogen and oxygen.
Yes. The answer is, the question was, how do you have to detect those different kinds of water? So basically, these are all polar molecules, so they have rotational, vibrational frequencies associated with them. If you look at HDO, hydrogen, deuterium, and oxygen, HDO has a rotational vibrational frequency at 509 gigahertz, very strong line. And then H217O is actually 548 gigahertz. Then 552 gigahertz. H218O is 548 gigahertz. Strongest water line is actually 557 gigahertz. So they have all these precise frequencies. So you'll have to develop the instrument so that you can measure very precisely those frequencies and what is the amplitude of the line. That will give you the abundance.
So this is kind of absorption spectroscopy?
That is exactly. These are the absorption spectroscopy.
Okay, thank you very much.
Prasanto, that's it. Teacher.
Hi, thanks for the nice talk. So I have a question. So when you have this ingenuity tested in Earth, how did you look for the dust profile of Mars?
Okay.
And did that make any problem in the ingenuity?
Yes. So we actually kind of trying to simulate what kind of dust conditions will be, but it is very difficult to simulate the dust conditions because we do not know what kind of dust conditions happen, right? What is the density of the dust and stuff. And it is a problem on Mars because the power source for this helicopter as well as many other rovers is solar panels. So if there is a dust storm, first thing that happens is the power. Power goes down. One of the things happened for this Spirit and Opportunity that one of the rovers actually does a dust storm and there is a thick layer of dust on the solar panels. And then it sent us a data saying that going in the hibernation mode. So it actually preserved itself and shut down all the systems and went into the hibernation. And then we are thinking, okay, maybe we have lost that rover. But after some time, suddenly we got a signal back saying, I am up. Because another dust storm came and we actually blew away all this dust and we started getting power again. So these things happen. We cannot really simulate everything, but we try to do as much as we can.
Who is it?
Just a curiosity that like we are sending all these probes, to see whether there is light molecules or say water also. What is the possibility that you might actually end up contaminating, like carrying the molecules from the Earth?
Yes, it's a very good question because we don't want to detect life by carrying life from here, right? So it is NASA has a very strict protocol of planetary protection. What we do is whenever we are making this spacecraft, we scrub it. We scrub it so well that there is no possibility of carrying any organic materials or any other kind of materials from here. So all of us will have to do that. Otherwise, we'll carry life from here to Mars and detect it there, right? So we make sure that that does not happen. So we go through, we have to spend a lot of money and effort. So we have a planetary protection team. Before they certify, before we launch anything. So you'll have to go through that protocol, they'll scrub everything, we go through. Every time I write a proposal, I'll have to write 2 pages of planetary protection scheme, how I am going to protect it so that I don't carry anything.
Yes.
Yeah, hello, sir. Yeah.
Yes.
Yeah. Sir, how do you save your delicate electronics from the harsh cosmic ray when it travels?
Yes, that is again a very good question. So there are 2 different aspects of it. One is when you're talking about radiation testing. One is TID, total ionizing dose. So as you know that when you are going to, in space, there is ionization coming in from cosmic rays and other things. And depending on the life of your mission, you can calculate, you can integrate what is the total ionizing dose you are going to get. It depends on where you are going. If you are going for low Earth orbit, you know that total ionizing dose should be about 25 kilorad or something like that to make sure that electronics survive that. But now if you are going to Europa is very close to Jupiter, as I said, and the radiation there is about 1 megarad. When you use X-ray, we are talking on millirad kind of range. So how do you protect that? One of the things that we have to do is, if you go for lower node electronics like 65 nanometer, 30 nanometer electronics, the CMOS circuits, they are immune to those radiation because the radiation misses it. However, most of electronics, they are higher node. So we'll have to shield them. One of the ways to shield is using thick lead boxes around sensitive electronics. But the problem there is more mass. We don't want to put more mass. Each kilogram of mass that we add to our spacecraft, it costs millions of dollars more. So we'll have to have strike that balance. Another thing in terms of radiation is ACU, single event upset. Basically, that could be a very high energy cosmic ray can come and disable your electronics. So our thing that we actually tested, like a place like VECC, that's where ISRO wants to come and work with you to test their equipment. Can it survive an ACU? single event upset. And we design it in a way, if we don't have a backup, then can you recover from there? Can you just reset? It is not a fatal event. So that's how we do it.
So thank you for the wonderful talk. Like you said that on the surface of Mars, we have a very stormy and dusty weather. So when ingenuity is going on the surface, so the wings of it, what material are you using, and can it be recovered if there are scratches?
So first of all, we have not brought anything back from Mars yet. So if there is scratches will be there on them. But of course, what we do is that very sensitive surfaces, like an antenna or optical, let's say we have an optical lens there. So we put coating on them so that, like my glasses has scratch-proof coating. So that even if I try to scratch it, it won't scratch. As, of course, not 100%, but as far as possible. So that's why some of these sensitive surfaces, we put scratch-proof material coating on them. So that's how we do it.
Hello, sir.
Yes.
First, I have two questions. First one is like water is gushing out of this planetary bodies. Do we see such event in our world, like in our art, like water coming out of the surface? Usually, is it a volcanic eruption kind of thing that you have shown that water will come out of the surface?
I didn't understand the question.
The water coming out of this planetary surface, no?
Yes.
You are going to detect.
Oh, okay. Enceladus that I showed. Okay. Yeah. Yes.
So, what is the phenomena behind it? Is it the volcanic eruption kind of thing?
So we still don't know, to be honest. But what we think that what is happening is that there is water is there, under the thick shell, but there is opening happens once in a while. And then Enceladus is very close to Saturn, right? Just like our moon, changes the tide on our Earth. Similar way, whenever the Saturn comes close to it, if there is a crack or something, then gravity pulls this out. So we do not know whether it's a volcanic activity or not, but we believe more to do with the gravitational activities.
Another is, as you said, that if it is covered with dust, can we not have this vibration kind of mode that it move away all the dust so that the solar cell can be protected from this dust?
I still even do not.
Again, if your solar cell get covered with the dust,
yes,
can we have this vibration kind of thing that it move away the dust and then it can again get the power?
We can do a lot of stuff. We can put a wiper on them, like your car, right? We can put everything needs power. So whenever you're building something, there could be a lot of different solutions. But question is that the right solution for you? If you look at the power that we can get in all this, if you are trying to vibrate something which weighs certain amount, it takes a lot of power. So you'll have to think about what is the best solution for that particular situation. Yes.
Thank you, sir. As far as I remember, there was one mission where a probe was crash landed on a comet recently. So, any outcome from there which would have helped with your mission?
Yes, that mission was Rosetta mission. Rosetta mission was a European ESA mission, and NASA had an instrument. We call it, actually in our lab we build that instrument. So they had a lander to go to the comet, 67P, the name of the comet. And what happened is that lander actually crash landed and went into a crevice. There was no sunlight, and it had solar panels. So as a result, it could not send any data back. So that was the thing that happened for that. It's so unfortunate, very unfortunate. But again, in the future, we'll have to guard against that. Even if actually it lands there, we are working on some of these things called wireless power transfer. In the sense that if there is a lander going there, And it happens that if you cannot see the sun for some reason, can we beam some electromagnetic energy so that it can actually convert from AC to DC and then charge their battery and do it. So there's some technologies that are being developed for that.
Excuse me.
Anyone?
Yes.
One question. You said about the water vapor sensor, and this is you talked about the frequencies of 500 gigahertz or something like this for specific bands, and at the same time you were much conservative about the use of power for your sensor. Now, instead of that, can you not use the laser sensors there, that is the overall spectroscopy? Because that conserves the power. I just recollect because in my PhD time, Ed Browell was there in JPL last time. So you are of one of my papers. So we had some conversation over this. Can we not use such kind of things?
Yes.
So is there something in plan for you?
I've answered. The question was that, okay, what about laser frequencies, a very high frequency? If you look at water molecule actually has multiple frequencies, vibration frequencies. One of the strong line is 183 gigahertz. And the next, basically, the strongest line is 557 gigahertz. However, there are lines in the optical frequencies as well, in the infrared frequencies as well. So when you are looking at this, making an instrument, so one first question before I answer your question will be that why not use 183 gigahertz? That is much lower frequency. It is easier to get components at this frequency. Problem is lower the frequency, we are always limited by physics of lambda over d. If you are trying to look at a smaller place, diffraction limited, the spot size will depend on lambda over d. If the lambda is large, it means your antenna size has to be larger and larger. So going at higher frequencies like 557 has an advantage that smaller antenna can give you still, diffraction limited beam spot smaller. And you go at the higher frequencies, we actually have built instruments at those, as you are talking about, and laser frequencies as well. Again, you'll have to look at how much total power is needed for that instrument. What is your back end, right? How do you get the data? One thing is look at the vibrational frequencies of at that frequency, like infrared. How do you convert that to an electronics that you can set the data back, right, at the end of. So those things all come in the way. So it is not a one solution, not a single solution. This is one of the solutions that seems to be pretty good solution. So we are looking at other solutions as well.
Thank you. Thank you. I think I have one question.
Go ahead.
You have shown you have shown a video where this very small waveguide
Yes.
dimension is getting changed automatically. But now the point is that there is a transition from this particular dimension to that particular dimension. There is an in between.
Yes.
So that condition, what is the frequency and how it is taken care of?
So yes.
Because there it is not a peak frequency because it is in the transition space, even if it is a microsecond or nanosecond like that.
Yes, so it's actually a very good question. So what happens is that how often and how fast you have to switch. It comes down to the requirements, right? So we do not really need to switch very fast. The reason is something called how stable is your instrument. Something we call it the Allen time. So if you look at radiometric equation, that how stable in the sense how often is changing. If you look at your amplifier, with time the gain changes. So you can calculate is your stability of that amplifier. How often you need to really calibrate, go back and calibrate. So what happens is, in this case, when it is switching back, there is a microsecond range where both the things are open at the same time, right? So we don't use that data. But we are losing data for microsecond when we are we are observing for hours. So the impact of that is pretty low.
But that does not destabilize your system.
It does not. When you are designing your system, you have to make sure that S11, the reflection coefficient, and everything that it does not go into the regime where it is unstable.
So that is
you have to take
that should not beyond that value.
Yes. So you have to design accordingly.
Any other questions? Yeah.
Hello, sir. Thank you very much for this talk. I don't know whether I can express my question correctly. So, actually, what I understood is that everything is limited by the power that we are sending. But from a layman's point of view, if we require a 100-watt machine, we will send a 100-watt system to a solar panel based system to power it. So, what limits this power capability that we are sending? Only the commercial aspect or anything technical aspect also?
Again, it's not really a commercial aspect because when you have a mission, let's say Perseverance rover mission, it costs $2 billion. They are not going to carry only my instrument. You never carry a single instrument. Suppose my instrument doesn't work after going there. So $2 billion mission is gone. So they will have at least 10 different instruments. So I require 10 watts of power. Someone else needs 30 watts of power. So you have to calculate how much total power that you need for different instruments. As I said, for outer planet missions, we have about 400 watts of power. Why 400 watts? Why not 1 kilowatt?
Actually, that's my question.
Yeah, why not 1 kilowatt? So how do we generate that power? We generate the power with solar panels. If you see the solar panel that is put on the roof here, the efficiency of those solar panels is about 20%, 17 to 20%. The solar panels that we use, their efficiency is about 37 to 40%. They're much more expensive. That's why you do not put them on your rooftop. But it depends on how much area that you need to put to generate that much of power. From the efficiency you can calculate. Now it adds mass, right? As I said, every kilogram of mass that you want to launch in outer space, it costs a lot of money. Bigger rockets, everything starts piling up. That's why whenever you are designing a mission, you start from there. Okay, what is the biggest solar panel I can put on? How much power I can generate? And okay, then we see the different instruments asking for different amount of power. If I go and say my instrument is 100 watts, they're not going to select my instrument because then it will take most of the powers. That's how it goes. And it is an optimization process.
Thank you.
Yeah, then behind.
So, thank you for the nice section. Actually,
Yes.
Go ahead.
Carry on.
You can.
Yeah. Okay. So thanks for this wonderful presentation. My question is only with regards to the next steps. So you showed very nicely about the flight endeavor of ingenuity. After that, what does NASA plan?
Okay, depending on how much money we have. So we are planning for the next generation of these helicopters to have different instruments. See, for the first one, it was a tech demo. We had just a few cameras and stuff, not many instruments on them to do actual science. But now we are planning to mount a GPR, ground penetrating radar, also some spectrometer instrument on those helicopters. So we are developing the next generation of that. Again, when you start thinking about it and then you see we need a bigger helicopter, we need more power. How do we generate the power? Shall we do wireless power transfer from the rover to the helicopter? It's possible. So all these things we are brainstorming right now. What is the next one we are going to do? But we already developed some concept. So depending on how much money we have in the future, I'll let you know.
Anyone else?
may I?
Yes.
Actually, I have this curiosity that what about thermonuclear batteries for outer space? That is that first step. Another one is that microwave-driven motors for propulsion.
Yes. So there are two questions. One of them is about RTGs. RTGs are actually we use them. We use some plutonium, basically radioactive material that generates the thermal power that converts into DC power. We use in few missions. One of them was Saturn mission that we did. We use that. But whenever possible, we try to avoid some of these RTGs. We have RTGs for these, the rover, the Perseverance rover and RTG, not a solar panel. So it is very safe. However, there's always a concern. Suppose we are going to go to a planetary body and trying to find life, and something happens with the RTG, that will be a disaster, right? So we actually, when we are trying to think about RTGs or solar panels, we discuss about all these different scenarios. So if we can use RTGs, that is the best option. Again, it's a limited amount that we can carry, right? So that was the first one. And the second question was? Yes, the electric propulsion system. We actually started building electric propulsion system, not chemical propulsion. One of the missions called Psyche that we launched late last year is going to an asteroid. And this asteroid, very interesting asteroid, because for it, all the outside materials have been stripped off. Like if you look at our planet, we cannot really go down that deep and find out how the mantle works. But this asteroid is very interesting. All the outer core is gone. What is left is the inner core, and mostly iron and nickel. So we are actually going there, and for that mission, we are using electric propulsion system. So for the first time, we are using electric propulsion on that. Yes.
Very easy question.
No questions are easy questions. Always tricky questions. Okay, go ahead, please.
Compared to Earth, what is the atmosphere composition in Mars?
As you said that the total density is much less. Martian atmosphere is very similar to ours in the sense that we have oxygen, but we are missing some, but the ratios of different composition is slightly different than ours. But otherwise, composition is very similar. That's why you call that in early history it's very similar to our planet Earth. That's the reason, because it actually developed very similar environment. But as the atmosphere was lower, because of the cosmic rays, we lost some of these quantities of some gases. And that's why the composition is slightly different from what we are, what it is on planet Earth.
Another thing, it is said that in the Mars, earlier there might be some water, which is not there at present. But if you, is it possible to bring some gaseous sample from Mars?
Yes.
To analyze whether any water vapor content is there. Because earlier if water is there, then in the atmosphere gas, there might be some strong level presence of water level.
Yes. So we knew at one point of time there was a lot of water on Mars. Now also we know that under the surface, we are actually measuring some of these, that under the surface there is some water. And there is different theories that what happened to the water of Mars, where did it go? But in the atmosphere, we have instrument that actually measures that atmosphere has water vapor, but the density is very low, right? Abundance is very low. So we can measure those things. So water is there, water vapor is there. Under the ground, we know there's still water, and theory is that what happened that some of these minerals, they absorb many of this water, and then they release. That's why there is one of the things that we can do. We actually try to go through the surface, penetrate the surface, and see how much water is there. But it all needs a lot of different experiments, and it's very expensive business. So always we are fighting that what is more important.
Thank you very much.
Yeah, I think last question.
I cannot hear. Come on.
Sir, you have seen that in your lecture that you have shown that overall temperature of the global, our planet, is increasing gradually from last 15 years. And now my question is the overall, what is the reason? This is based on only activity what we are doing inside in our planet, or there is a contribution from the overall other planets on the galaxy?
No, this is.
Overall temperature also other planets increasing or not? That is my
So the question was that what is the reason for the change of surface temperature, for globally? We are the reason. That is clear evidence. This is man-made activities. that is the reason global temperature is changing. So there is absolutely no doubt in the scientific explanation. The political explanation will be different, and I don't want to go into those, but scientifically, there is irrefutable evidence that man-made activities, use of the fossil fuels, they are causing the change of the temperature and extreme event that we are seeing. We are the reason.
Temperature of the other planets also not increasing for last
I know, because people are not going there and creating driving cars there.
Sir, just I have a question connected to that. As you are saying that man-made global warming.
I call it climate change, yes.
Okay. But in case of Mars, as you are telling that there is a natural warming. But you are telling that there is a probably traces of water on the surface, but there are nothing there till now. So there are also warming is going on. But so man-made is not the only one, no?
No, I'm not the only one who's saying it. What I'm saying is that there is a natural, that as the climate changes in thousands of years, right? And we are looking at the change of global temperature change in less than 100 years. So there is a difference. So as a scientist, scientific mind will have to look at the data. Data does not lie.
Okay, thank you very much.
Thank you, sir.
For this illuminating talk. And so I think
Please stand on stage. Thank you very much, sir, for such a wonderful lecture. And now let me invite Dr. Rup Bandyopadhyay, Chairman of the Organizing Committee, as we are starting the Health Station program. I request Rup sir to present a flower bouquet to Dr. Gautam Chattopadhyay. Mr. Ani Majumdar is requested to help. Director of VECC, Dr. Sumit Sum is requested to honor the speaker with an superior. Mr. Samrita is requested to help. Another tradition with Ramanna Memorial Lecture is the citation to the speaker. Director sir is requested to read and present the citation. Mr. Ani and Mr. Shamrita.
first I read the citation from here, although it is So this citation presented to Dr. Gautam Chattopadhyay, Senior Research Scientist, NASA, Jet Propulsion Laboratory, California Institute of Technology, USA. On the occasion of the 19th Ramanna Memorial Lecture entitled Space Exploration and Our Place in the Universe, delivered at the Meghnad Saha Auditorium, SINT VECC campus on July 29, 2025, in recognition of his outstanding and inspiring lecture that illuminated the wonders of space exploration and its profound implications for science, technology, and our understanding of the universe. With deep appreciation for his pioneering contributions to the development of advanced space instrumentation, his visionary leadership, and his commitment to fostering scientific curiosity across generations. We are honored by his gracious presence and grateful for the insights he has shared, which reflect the true spirit of inquiry that Dr. Ramanna stood for. Presented with warm regards and admiration. Thank you. So this is the citation I have already read.
Dokra art is one of the examples of tradition and handicraft of Bengal. I request Director Sir to present the Dokra idol of Ma Durga as a memento to Gautam Sir. Mr. Samriddha to help.
Thank you very much.
Thank you very much, sir. Dignitaries on the dais, I request you to take their seats in the audience. I request Dr. Sarveshwar Bhattacharya, member of organizing committee, for a vote of thanks.
So it is my duty now to give the vote of thanks. Without this, any of the events cannot be completed. So we would like to first of all thank our esteemed speaker, Dr. Gautam Chattopadhyay, for his enlightening lecture on this very interesting topic of current interest. I am sure there are a lot of questions already still in our mind, and more questions and curiosities will come in coming future. And we are also thankful to our director VECC, Dr. Sumit Shom, who actually supported active support for this event and organizing this special event, and for his guidance to organize this today's program. And we thank all our special invitees and faculties for their precious presence in this event, and all our VCC employees and colleagues, and all the participants for today's program. We thank all our former employees who have joined today physically and also online to this program. And we thank all our students, HVNI students and trainees for joining these events and actively participating in this event for organizing this program. And we are also very much thankful to press and media for their coverage and who help us to share the message that our speaker has conveyed today. We are thankful also to the authorities of SINP, Director SINP, for providing this auditorium to organize this event. We thank SINP for all logistic support for today's program. And we are thankful to SINP Securities and the VCC Securities as well for managing all other logistic supports. And we are thankful to the garden people of VCC, accounts, transport, and canteen. Without their help, all the organizing these events were not possible. And lastly, thanks to all the members of the organizing committee, Dr. Vaishali Nayak for preparing the press release, and Tanmoy, Shujit, and Ranini, Neeraj, and Jayanto, and all the HVNI students for participating in this event and also organizing this event. And not the least, I also thank Partho and Monirul, just always be there in the back of the stage for releasing the whole program in the YouTube all the time. Okay, thank you all once again for being with us in this very special event.
धन्यवाद सर्विस स्टूडेंट। कार्यक्रम के अंतिम चरण में आप सभी से अनुरोध है कि अपने स्थान पर राष्ट्रगान के लिए खड़े हो जाएं। गान का नेतृत्व करेंगे डॉक्टर जय देवता तथा उनके साथ एसबीएनआई के विद्यार्थी सुश्री अंकिता मजुमदार, सुश्री मधुस्मिता वर्मा तथा सुश्री हेमंती मंडल।
Ah
अंत में केंद्र निदेशक की अनुमति से इस सभागार का कार्यक्रम यहीं समाप्त होता है। आप सभी को बहुत धन्यवाद।